Time itself grinds to a halt at the edge of a black hole. This is the startling truth we will unpack, revealing how gravity warps the very fabric of reality. By the end, you will understand why time is not a universal constant, but a personal experience shaped by the cosmos. We will see how an astronaut could fall into oblivion in seconds, yet appear frozen at the brink from our point of view. What does this cosmic contradiction say about the nature of our own reality? This profound idea came from a mind that dared to rethink everything. In the early 20th century, Albert Einstein challenged the very bedrock of physics. For centuries, thinkers from Newton onward viewed space as a fixed, empty stage and time as a universal, unchanging clock. They were separate and absolute. But Einstein saw a deeper connection. He proposed that space and time are not independent. They are interwoven into a single, dynamic entity he called spacetime. Think of it not as a stage, but as the fabric of the cosmic arena itself. This fabric is not rigid. It is flexible, like a vast, invisible trampoline sheet stretched across the universe. Now, what happens when you place a heavy object on a trampoline? It creates a dip, a curvature. Einstein's genius was in realizing that massive objects, like our Sun or Earth, do exactly this to the fabric of spacetime. They create dents, and gravity, that mysterious force that pulls us down, is not a force in the traditional sense at all. It is simply the result of objects moving along the curves in this warped fabric. A planet orbiting a star is not being pulled by an invisible string. It is like a marble rolling around the rim of the dip made by a bowling ball on that stretched sheet. It is following the shape of the arena. This curvature explains the paths of planets and the bending of starlight, but it does something even more incredible. It warps time itself. This is gravitational time dilation. The closer you are to a massive object, the deeper you are within its gravitational well, the slower time flows for you compared to someone farther away. It is not a mechanical clock error. It is a fundamental property of reality. Your personal experience of time, the ticking of your very atoms, is shaped by the geometry of the space you occupy. On Earth, this effect is incredibly tiny, measurable only with the most precise atomic clocks, but it is real. It means a clock on the ground ticks very slightly slower than a clock on a mountaintop. Now take this concept and push it to the ultimate extreme. Place an object so unimaginably dense that it creates not just a dip in spacetime, but a pit so deep and steep that nothing, not even light, can climb out. You have created a black hole, and at its edge where the curvature becomes infinite, the warping of time does not just slow, it stops. This invisible boundary is the event horizon. It is the ultimate point of no return, a mathematical line drawn in the fabric of spacetime itself. If you picture a black hole as a cosmic whirlpool, the event horizon is not the water, nor the swirling debris. It is the precise, unseen edge where the current becomes so overpowering that escape is impossible. Nothing that crosses this threshold, not a single particle of light or a shred of information, can ever communicate with the universe outside again. It is a one-way door from the reality we know into a realm of profound mystery. The size of this boundary, what physicists call the Schwarzschild radius, is determined by one thing alone: the mass of the black hole. For a non-rotating black hole, this is the distance from the center at which the escape velocity mathematically equals the speed of light. Since nothing can travel faster than light, the conclusion is absolute. But the event horizon is not a solid shell you could bump into. It is a property of space, a condition of such extreme curvature that the paths leading outward all twist back inward. And it is right here, at this invisible frontier, that time itself begins to behave in ways that defy all intuition. setting the stage for the profound paradoxes we are about to witness. This subtle warping of time is not just theory, it is a measurable fact of our universe proven right here on Earth. The phenomenon is called gravitational time dilation. The deeper you sit within a gravitational field, the slower your personal clock runs relative to someone higher up. It is as if time itself flows more sluggishly under greater weight. We can confirm this with astonishing precision. Atomic clocks, the most accurate timekeepers ever built, tick at detectably different rates when placed at different altitudes. A clock at sea level, feeling the full pull of Earth's gravity, will lag ever so slightly behind an identical clock on a mountaintop. Over many years, the difference would add up to a tiny fraction of a second. The effect is minuscule in our daily lives, but its existence is profound. It tells us that time is not a universal metronome ticking in the void. It is a local experience, a personal rhythm dictated by the geometry of the space you occupy. Now take this proven concept and amplify it beyond all earthly scales. Approach the most intense gravitational field imaginable, the edge of a black hole. Here, the slowing of time does not remain a subtle scientific curiosity. It escalates into a cosmic spectacle. As an astronaut falls toward the event horizon, the gravitational pull they feel becomes unimaginably strong. To us, watching from a safe distance with powerful telescopes, their descent would begin to look strange. Their clock, their heartbeat, every process that marks the passage of time would appear to us to slow down. Not by microseconds, but dramatically. Their fall would seem to decelerate as they neared that invisible boundary. From our vantage point, they would approach the event horizon more and more slowly, their image reddening and dimming as the light struggles to escape. Mathematically, from our perspective, their clock would tick infinitely slowly as they reach the very edge. They would appear to us not to cross the horizon, but to hover there, frozen in a final moment for all eternity. It is a breathtaking illusion, a trick of spacetime geometry. For the astronaut, their own clock ticks normally. They would feel nothing special at the moment of crossing, and from their point of view, would pass the point of no return in a finite amount of time. Yet the universe outside would forever tell a different story, one where time at the edge has simply stopped. How can two realities, the astronauts and ours, be so violently at odds? The answer lies in the nature of light and information, and a paradox that threatens to unravel physics itself. This creates a cosmic paradox where two truths exist simultaneously. For the astronaut, the journey inward continues. Their own senses and instruments would report nothing unusual as they cross the event horizon. If the black hole is large enough, the tidal forces at that boundary might even be gentle. In their own frame of reference, their clock ticks forward 1 second at a time. They would pass the point of no return in what feels like a finite, and perhaps surprisingly brief, amount of personal time. From their perspective, the universe behind them does not freeze. They could, in theory, look back and see the stars of the galaxy receding as they fall further in. Their reality is one of continuous motion. Yet for us, the distant observers with our telescopes trained on this event, the story is utterly different. We would witness a profound and eerie transformation. As the astronaut approaches the event horizon, the light escaping from them has to climb out of an immense gravitational well. This struggle steals the light's energy, stretching its wavelengths. To our eyes, the astronaut's image would shift from white to orange to a deep, dim red, and finally into the invisible infrared. At the same time, each successive signal, each photon, takes longer and longer to reach us. The astronaut's movements would appear to slow down like a film played at 1% speed. Their final approach to the horizon would seem to stretch out over years, centuries, millennia. Mathematically, from our vantage point, they never quite cross. They become a fading, reddened ghost, frozen forever at the brink. This is not a trick of the lens or a delay in signal. It is the direct consequence of time itself flowing at a different rate for them than it does for us. The extreme curvature of spacetime near the black hole stretches the interval between ticks of their clock to infinity from our point of view. Both perspectives are equally valid. There is no single, privileged clock for the universe. Time is relative. Your experience of its passage is a deeply personal affair, woven from the fabric of your own motion and the gravitational landscape you inhabit. This realization forces a profound question. If the astronaut crosses the horizon from their view, but forever hovers just outside it from ours, then what is the true nature of that boundary? The answer leads us to one of the most heated debates in modern physics, a conflict over information, firewalls, and whether the laws of reality break down at the edge. This mathematical stretching of time has a direct and visible consequence, a ghostly fade to black. As our astronaut nears the event horizon, the light they emit faces a desperate climb. Each photon must fight its way out of the black hole's immense gravitational pull, and that struggle costs energy. The light's wavelength gets stretched, shifting its color down the spectrum. From our distant vantage point, we would see their suit shift from brilliant white to a dull orange, then to a deep crimson red. The image grows dimmer as fewer photons manage the escape. And as they approach that final mathematical boundary, the redshift becomes infinite. The wavelength stretches toward a length we cannot measure, shifting the light completely out of the visible spectrum and into the realm of radio waves, then beyond any detection. To our eyes and instruments, the astronaut does not vanish with a pop. They simply fade away like a star dimming at the end of the universe. This infinite gravitational redshift is the observational signature of infinite time dilation. It is not two separate effects, but one unified truth seen from different angles. The same extreme curvature of spacetime that grinds the astronaut's clock to a halt from our perspective also saps the very energy from the light they send us. The fading image and the frozen motion are two sides of the same coin, a direct testament to how gravity manipulates the fundamental fabric of reality. It warps space, bends the paths of light, and dictates the tempo of time itself. Yet this flawless mathematical picture creates a profound and troubling puzzle for physics. If the astronaut is forever frozen at the edge from our view, but has long since passed it from their own, where is the truth of their experience? This question leads us to the edge of a different kind of abyss, a conflict in our understanding of reality so sharp it has been called the greatest crisis in theoretical physics. Yet the event horizon is not the only boundary of terror. Long before an object reaches that point of no return, the sheer gradient of gravity becomes a destructive force in its own right. This process has a vivid, almost culinary name, spaghettification. It describes what happens when the difference in gravitational pull across an object becomes too extreme to withstand. Imagine our astronaut falling feet first toward a stellar mass black hole. Their feet, being slightly closer to the black hole's center, feel a significantly stronger tug than their head. This difference in force, the tidal force, creates an immense stretching effect. It is like being on a cosmic rack, pulled longer and thinner with every passing moment. The body and any spacecraft around it would be stretched into a strand of matter, a gruesome yet inevitable outcome of crossing such a severe gravitational slope. But this is more than a violent reshaping in space. There is a temporal dimension to this destruction as well. Because the feet are deeper in the gravitational well, time for them flows even slower than time for the head. From the perspective of a distant observer, the astronaut's feet would appear to age more slowly than their shoulders. The object is not just being pulled apart across distance, it is being pulled apart across time itself. Different parts of the same person would exist in slightly different rates of the universal clock. This is perhaps the most visceral demonstration of gravity's gradient, a force that warps the arena of reality so severely that it distorts both the container and the clock within it. For supermassive black holes, the event horizon is so far from the central point that the tidal forces at the boundary can be surprisingly gentle. An astronaut might cross it without immediately noticing. But for smaller, denser black holes, spaghettification would occur well outside the event horizon, a stark reminder that the edge of a black hole is a zone of radical physics, where the familiar rules of a unified self and a single timeline begin to unravel long before the final threshold is crossed. But the black holes we have been picturing are a special, simplified case. Reality is far more dynamic. Most black holes in the cosmos are not still. They spin, often at a significant fraction of the speed of light, born from the furious rotation of the collapsing stars that forged them. These are described by a different mathematical model, the Kerr metric, and they twist the fabric of reality in an even more bizarre way. The rotation of the black hole does not just create a dent in spacetime. It stirs it. This effect is known as frame dragging. Picture spacetime not as a static trampoline, but as a vast, cosmic ocean of honey. Plunge a spinning sphere into that honey, and the viscous fluid around it begins to swirl, caught in the motion. A rotating black hole does exactly this to the fabric of the universe around it. It grabs spacetime itself and drags it along in a relentless, cosmic whirlpool. This creates a bizarre new region outside the event horizon called the ergosphere. It is an oblate, pumpkin-shaped zone where the twisting of spacetime is so powerful that nothing, absolutely nothing, can remain at rest. The very fabric you are sitting on is moving. To resist being swept along, you would have to move faster than light in the opposite direction, which is impossible. Within the ergosphere, you are compelled to rotate with the black hole, a prisoner of its gravitational vortex, and this profound twisting does something extraordinary to time. Within the ergosphere, the paths that particles and even light can take become entangled with the black hole's rotation. The flow of time here is no longer simply slowed by gravity. It becomes directional, tied to the spin. Moving with the rotation, time may flow one way. Attempting to move against it could lead to even stranger consequences. This sets up incredible possibilities like the Penrose process, where an object could enter the ergosphere, split apart, and one piece could be flung out with more energy than it entered with, essentially stealing rotational energy from the black hole itself. But for our understanding of time, it introduces a new layer of complexity. Time at the edge of a spinning black hole is not just frozen. It is corkscrewed, woven into the very vortex of spacetime, making the distinction between past, present, and future even more fluid and dependent on your path through this twisted geometry. But before matter meets its final fate at the event horizon, it must first navigate a cosmic point of no return. Just outside the black hole, there exists a critical boundary of pure orbital physics, the innermost stable circular orbit. Often called the ISCO, this invisible line marks where the familiar rules of orbital motion finally break down. For a simple, non-spinning black hole, this orbit sits at precisely 3 times the Schwarzschild radius, the radius of the event horizon itself. It is the ultimate cosmic racetrack, the last possible parking spot for anything trying to orbit a black hole without falling in. Think of it like trying to pedal a bicycle on the inside wall of a giant, smooth funnel. Get too close to the center and the slope becomes too steep. No matter how fast you pedal, you cannot maintain a circular path. You will inevitably spiral downward. The ISCO is that precise point on the funnel wall where a stable circular orbit is just barely possible. One tiny nudge inward, one slight loss of energy, and the object's fate is sealed. It transitions from a stable orbit into an unstoppable, inward plunging trajectory toward the event horizon. This boundary is not defined by the black hole's pull alone, but by the fundamental geometry of spacetime as described by general relativity. Newtonian gravity, which governs our solar system perfectly well, predicts that orbits can exist at any distance from a mass, provided you have the right speed. But near a black hole, the extreme curvature of spacetime introduces a radical new rule. The warping is so severe that it destabilizes circular motion below a certain distance. The ISCO is the point where the stabilizing influence of orbital motion is exactly balanced by the relentless space-time warping pull of the black hole. It is a line drawn by gravity itself, separating the realm of possible orbits from the realm of inevitable doom. For an object circling at the ISCO, the effects of relativity are not subtle curiosities. They are overwhelming. The orbital speeds required are a significant fraction of the speed of light, and the passage of time for that object is already drastically altered. An astronaut in a ship holding a perfect orbit at the ISCO would experience profound gravitational time dilation. Their clock would tick far slower than the clocks of colleagues observing from a safe, distant station. They might complete a few orbits, watching years or decades pass for the outside universe in what feels like mere hours for them. This orbit is not just a boundary in space. It is a threshold in time. It represents the final outpost of normal, if extreme, physics before the final descent into a region where time's behavior undergoes its most dramatic and irreversible transformation. The matter we often see glowing in accretion disks around black holes, the brilliant swirls of superheated gas, is dancing right at this precipice. The ISCO is where the last light from stable matter is emitted before it vanishes from our view, crossing over into the dark, where time itself begins to unravel completely. The brilliant glow surrounding many black holes is not the monster itself, but its last supper. This swirling, superheated maelstrom of gas and dust is an accretion disk, a cosmic whirlpool where matter makes its final, luminous descent. Far from just a pretty light show, these disks are among the most extreme natural laboratories in the universe. They are places where the abstract predictions of Einstein's theories become visible, tangible realities etched in light. Within that furious whirl, particles are not just falling. They are orbiting at a significant fraction of the speed of light, caught in a frantic dance just outside the point of no return. This creates a perfect storm for distorting time. Two powerful effects combine here. First, there is the special relativistic time dilation from their incredible speed. Just as a clock on a fast-moving spaceship ticks slower, so do the processes for these hypervelocity particles. Second, and even more powerfully, there is the general relativistic time dilation from the immense gravity of the black hole they are circling. The inner edge of the disk, brushing against the innermost stable circular orbit, is where this combination reaches a fever pitch. Time for that searing hot gas flows at a rate drastically different from our own. This distortion is written directly into the light that escapes to us. Photons battling out from that inner chaos are robbed of energy, their wavelengths stretched to the red. The variability of the light, its flickers and flares, appears to us in slow motion, like watching an explosion through a lens of thick, distorting glass. By meticulously decoding this light, by analyzing its spectrum and timing its pulses, astronomers perform a kind of cosmic forensics. They are not just looking at hot gas. They are reading the fingerprints of warped spacetime itself. Each redshifted measurement, each slowed-down flicker, is a direct test of relativity's most radical prediction. We are using light as a probe to witness, from a safe distance of millions of light years, how time itself falters and bends at the edge of eternity. This profound contradiction between two pillars of physics creates a crisis known as the black hole information paradox. On one side, we have quantum mechanics, the rulebook for the very small. It insists that information is never truly destroyed. The exact quantum state of every particle that falls into a black hole, its unique identity, must be preserved in some form. It can be scrambled, hidden, or transformed, but never erased from the universe's ledger. On the other side stands general relativity, which paints the event horizon as the ultimate one-way street. From its perspective, anything that crosses that line is lost forever to the outside cosmos, its information sealed behind a curtain of infinite time dilation. Both theories are spectacularly successful in their own domains, yet they offer two completely incompatible stories about the fate of what falls in. This is not a minor accounting error. It suggests that at the very edge of a black hole, our fundamental understanding of reality, of how time progresses and causes lead to effects shatters into pieces. If information is truly lost, then the orderly flow of time and causality as we know it could break down. The universe would become unpredictable at its most basic level. To resolve this, physicists have proposed ideas that sound like pure science fiction. One of the most compelling is the Holographic Principle. It suggests that all the information about the three-dimensional volume inside a black hole is not lost, but is instead perfectly encoded on its two-dimensional surface, the event horizon. Think of it like a cosmic DVD. The movie you watch is a rich, three-dimensional world with depth and motion, but all the data needed to create that experience is stored on the flat, two-dimensional surface of the disk. In this radical view, the event horizon is not a simple boundary. It is a buzzing, pixelated screen, with each tiny plank-sized area holding a bit of information about what fell inside. The three-dimensional interior, with its stretched time and warped space, emerges from the information painted on that two-dimensional surface. This leads to a staggering implication for time itself. If the flow of time and the experience of falling inward are not fundamental, but emergent properties that arise from how information is processed on the boundary, then time as we feel it may be a kind of illusion. It might be a consequence, not a cause, of more fundamental quantum interactions at the edge of reality. The strange freezing of time we witness from the outside could be a shadow of this deeper, information-based process. Solving the information paradox is not just about saving data. It is about discovering whether time itself is a primary feature of the cosmos, or merely a secondary story written on the boundary of things we do not yet fully understand. Yet even the timeless void of a black hole is not immune to the restless quantum world. Stephen Hawking made a startling discovery that forever changed our view of these cosmic titans. He realized that black holes are not perfectly black. They can glow, emitting a faint whisper of radiation. The key to this lies in the bizarre nature of empty space itself. At the quantum scale, what we call a vacuum is not truly empty. It is a seething sea of potential, a quantum foam where pairs of particles and their antiparticles constantly flicker into existence, borrowing energy from the universe for an unimaginably brief moment before colliding and vanishing back into nothingness. This dance of virtual particles happens everywhere all the time. Normally, they annihilate each other so quickly we never detect them. But place this quantum froth right at the edge of an event horizon, and something extraordinary can occur. In that zone of extreme warped spacetime, one of the virtual particles might be created just on the cusp, while its partner appears just inside. The particle inside falls irrevocably into the black hole, but the particle outside, suddenly robbed of its partner to annihilate with, finds itself real. It escapes, carrying away a tiny bit of energy. To a distant observer, this stream of escaped particles looks like a faint thermal glow emanating from the black hole itself. This is Hawking radiation. It is not fire or light from within the hole, but a quantum theft born at its very boundary. The energy for this radiation comes from the black hole's own mass. Every time a particle escapes, the black hole loses a minuscule amount of its substance. Over timescales that dwarf the current age of the universe, a solitary black hole would slowly, inexorably evaporate away. This introduces a profound new arrow into the story of black holes, a thermodynamic arrow of time. A black hole with Hawking radiation has entropy, a measure of disorder, and it evolves. It has a temperature, however cold, and it has a finite lifetime on the grand cosmic clock. It is no longer a timeless, eternal fixture. It is an object with a past, a present, and a future that ends. Hawking's work wove together gravity, quantum mechanics, and thermodynamics in a way that suggests even the darkest, most timeless corners of reality are subject to change and decay, governed by the same universal tick of time that governs us all. Beyond the event horizon, the journey does not end. It enters a realm of pure theory, a descent toward the singularity. This is the mathematical heart of the black hole, a point predicted by our equations where density becomes infinite and the curvature of spacetime becomes infinite. All the mass of the collapsed star is crushed into a volume of zero size. Here, the very tools we use to understand the universe, general relativity and quantum mechanics, cease to function. They scream in contradiction. The concepts of here and now, of distance and duration, simply dissolve. It is not just that time slows down. At the singularity, the fabric of spacetime itself ruptures. For the astronaut falling inward, this point represents a finite end to their world line, a final moment where physics as we know it reaches its ultimate limit. But what does that even mean? Some interpretations suggest that at the singularity, the distinction between space and time could invert. What was a direction through space could become a direction through time, and vice versa. A path inward might transform into a path toward a new kind of future, or perhaps a different kind of past. This is where our reliable map of reality tears at the edges, revealing blank spaces marked only by question marks. And for a rotating black hole described by the Kerr solution, the plot thickens considerably. The singularity in such a beast is not a point. The mathematics suggest it could be shaped like a ring, a loop of infinite density spinning at the center. This ring singularity is not hidden behind the event horizon in the same way. The equations paint a bizarre picture where, if you could navigate the chaotic twists of the inner ergosphere, you might theoretically pass through the ring's center without hitting the infinite density itself. And this is where the equations take a truly speculative leap. Some solutions to Einstein's field equations suggest that the region inside a rotating black hole could connect to a different spacetime entirely. The ring might act as a gateway, a tunnel through the fabric of the cosmos, what we popularly call a wormhole. These theoretical bridges could connect two distant points in our own universe, or even more fantastically, bridge the gap to a completely separate universe with its own laws and history. If such structures are possible, and that is a monumental if, they would not be gentle subway rides. The tidal forces and radiation would likely be unsurvivable, and the stability of such a wormhole is highly questionable, requiring exotic forms of matter with negative energy to hold it open. But the theoretical implication is staggering. It forces us to reconsider the ultimate purpose of the extreme warping we see at the event horizon. That slowing and freezing of time from an outside view might not be a dead end. It could be the outer door to a corridor where the rules are rewritten. Within such a wormhole causality, the law that cause must always precede effect could become malleable. Time ordering might not just be stretched thin, it could be looped, reversed, or transcended altogether. You could, in principle, emerge from such a tunnel at a point in time before you entered. This isn't just science fiction. It's a direct, if highly speculative, consequence of taking our best equations to their absolute limits. While we have no evidence that such wormholes exist in nature, their possibility in the math reminds us that the freezing of time at the black hole's edge might be the prelude to a far stranger symphony, one where the universe itself is woven with threads that connect not just places, but different moments and perhaps different realities. The ultimate test of these ideas lies not in theory, but in the cold, hard light of observation. While sending a probe to a black hole remains a distant dream, astronomers have become cosmic detectives, using the universe itself as their laboratory. Their prime target sits at the chaotic heart of our own Milky Way, a supermassive black hole named Sagittarius, a star. This invisible giant, weighing in at over 4 million times the mass of our Sun, is surrounded by a frantic dance of stars on razor's edge orbits. By tracking these stars for decades with powerful telescopes, scientists have witnessed a direct confirmation of Einstein's warped spacetime. They have measured the precession of these orbits, a subtle wobble where the closest point of a star's elliptical path slowly rotates around the black hole. This is not something Newtonian gravity predicts. It is a fingerprint of general relativity, a sign that these stars are moving through curved spacetime, not flat space. But what about time itself? Detecting the actual slowing of time from such a distance is incredibly difficult, yet the light from these stars carries telltale clues. As a star makes its closest, fastest pass by the black hole, the light it emits must climb out of that deep gravitational well. Just like our thought experiment with the astronaut, that light gets stretched. Its color shifts toward the red end of the spectrum. In 2018, after a 16-year observing campaign, a team announced they had finally measured this gravitational redshift from a star called S2 during its closest approach. The starlight had changed color exactly as Einstein's equations predicted. It was not a dramatic, visible reddening to the human eye, but a precise shift in wavelength that served as a proxy, a cosmic messenger reporting back on the severe warping of time in that extreme region. Each photon that reached our telescopes was a little older, a little more tired, because time where it began flowed more slowly. We are now entering an era where these indirect tests are becoming direct imagery. The Event Horizon Telescope, that global network of radio observatories, made history by capturing the first image of a black hole's shadow in the galaxy M87. That iconic orange ring of light is not the event horizon, but the photon ring, the warped path of light from the hot accretion disk bending around the black hole's dark interior. This image is a map of extreme gravity. Future advancements with more telescopes and sharper resolution aim to do something even more extraordinary. They hope to capture movies of matter orbiting close to the event horizon of Sagittarius, a star itself. We could watch blobs of hot gas complete their orbits not in minutes, as they would in flat space, but over the course of an hour or more, their motion visibly slowed by time dilation from our perspective. We would be witnessing in real time the very phenomenon we have been exploring, the gravitational manipulation of time written in the slow, graceful dance of doomed matter. These are not just pretty pictures, they are rigorous, data-driven tests confirming that the bizarre predictions about time at the edge of a black hole are not mathematical fantasy, but an active, governing principle of our cosmos. These observations from the edge of a black hole are more than scientific data. They are a mirror held up to our deepest assumptions about reality. If two observers can experience the same event in such violently different ways, one seeing a frozen statue of an astronaut, the other feeling a smooth, finite fall, then which story is true? The unsettling answer is that both are. This relativity of simultaneity shatters the comforting idea of a single, universal present moment that everyone shares. There is no cosmic clock in the sky ticking off a now for the entire universe. Your now is yours alone, woven from your position and motion through the gravitational landscape. The steady, uniform flow of time we feel in our daily lives is not a fundamental feature of the cosmos. It is a local, low-gravity illusion, a gentle fiction that only holds true in the relatively flat and quiet backwaters of spacetime where we happen to live. In the violent whirlpools around black holes, that fiction falls apart, revealing a much stranger underlying structure. This has led some physicists and philosophers to a radical view called the block universe. In this picture, the cosmos is not a story unfolding moment by moment. It is a static, four-dimensional block where all of spacetime, every event from the Big Bang to the distant future, exists eternally. Past, present, and future are all equally real, fixed in place like frames in a film reel. Our conscious experience, with its vivid sensation of a flowing now and a receding past, is not moving through time. Instead, it is a process that illuminates different slices of this eternal block, one after another, creating the persistent illusion of passage. A black hole, with its extreme warping, acts like a cosmic magnifying glass on this idea. The infinite time dilation we see from the outside is not a process happening in time. It is a permanent feature of the geometry, a frozen tableau written into the fabric of the block. The astronaut is both forever at the edge and long past it, depending on which world line, which slice of the block you examine. This is not a paradox to the universe, only to our intuition, which evolved to navigate a world of medium-sized objects moving at slow speeds. The black hole forces us to confront the limits of that intuition. It shows us that reality, at its most fundamental level, does not care for our human-centered concepts of before and after, of change and permanence. It simply is. Our journey to understand these cosmic extremes becomes, ultimately, a journey to understand the nature of our own experience, and to humbly accept that the true shape of the cosmos may be far grander and more mysterious than the story our senses tell. The mathematical heart of a rotating black hole holds a secret even more bizarre than a gateway to another universe. It suggests the possibility of a loop in time itself. Within the complex equations describing these cosmic whirlpools, physicists find theoretical pathways known as closed Timelike curves. The name sounds technical, but the idea is simple and profoundly unsettling. A closed Timelike curve is a path through the warped fabric of spacetime that circles back to its own beginning. If you could follow such a path, you would not travel to a new place in space. You would travel to a previous moment in your own history. You could, in principle, encounter your younger self. This is not science fiction plot logic. It is a direct, if highly speculative, consequence of taking Einstein's equations for a spinning black hole to their absolute limit. The extreme twisting of spacetime in the region inside the event horizon, particularly around a ring singularity, could theoretically twist the dimension of time into a knot. In this distorted landscape, the future on one path could bend around to become the past on another. The arrow of time, which for us always points forward, would here curl into a circle. Now, it is crucial to understand that most physicists believe closed time-like curves cannot exist in our real universe. The consensus is that quantum effects, which govern the very small, would prevent such loops from forming. They would create catastrophic instabilities or require impossible conditions, like matter with negative energy, to remain open. Many see them as mathematical artifacts, not physical possibilities. Yet their mere presence in the solutions to our most successful theory of gravity is a profound revelation. It tells us something essential about the relationship between gravity, time, and cause and effect. General relativity, at its core, is a theory about geometry. It describes how mass and energy shape the stage of spacetime. Closed time-like curves show that the geometry this theory allows can become so twisted that the sequence of events, what we call causality, loses its fundamental order. The equations do not inherently forbid you from being both the cause and the effect of the same event. This connects the frozen time we observe at the black hole's edge to the deepest puzzles of all. That infinite slowing from an outside perspective is a milder symptom of the same spacetime warping that, in theory, could fold time back on itself. It highlights that gravity is not just a force that pulls. In its most extreme form, it is the architect of time's very structure, and in sculpting that structure, it can create shapes that defy our every intuition about how reality should flow. The existence of these theoretical loops forces us to ask if the forward march of time is a universal law, or simply a local condition of the relatively calm cosmic neighborhood we inhabit. It suggests that at the boundaries of the known, where gravity reigns supreme, the universe may play by rules that render words like before and after completely meaningless. This line of thinking leads to one of the most profound ideas in modern physics, the holographic principle. It suggests that our experience of a three-dimensional world with depth and volume might be a magnificent illusion. The principle states that all the information contained within a region of space can be perfectly encoded on its lower dimensional boundary. Think of a credit card security hologram. The flat, shiny sticker holds no real depth, yet it projects a startlingly realistic three-dimensional image when you tilt it. The holographic principle proposes that our universe might work in a similar, though far more fundamental, way. For a black hole, this idea resolves the information paradox elegantly. The entire three-dimensional interior, with its warped space and stretched time, could be completely described by quantum bits of information dancing on its two-dimensional surface, the event horizon. Nothing is truly lost inside, because everything that happens within is mirrored in a complex code on the boundary. But what if this isn't just a clever trick for black holes? Some physicists, like Leonard Susskind, boldly extend the principle to the cosmos itself. They propose that our entire universe, with all its galaxies, stars, and planets, might be a holographic projection from a two-dimensional surface at the edge of everything we can observe. This is not a simulation in the digital sense. It is a statement about the fundamental ingredients of reality. In this view, the three spatial dimensions we move through are not primary. They emerge from the intricate quantum interactions happening on that distant cosmic boundary, and this has a staggering implication for time itself. If space is emergent, then time, which is woven together with space as spacetime, might be emergent as well. The steady, flowing time we feel in our bones, the relentless tick of the clock, may not be a fundamental feature of the cosmos. It could be a secondary phenomenon, a collective story that arises from the way quantum information is processed and related on that lower dimensional surface. The bizarre freezing of time we witness at the black hole's edge is not a glitch in the matrix. It could be a direct clue, a place where the illusion wears thin, revealing the more basic, timeless quantum processes underneath. In a holographic universe, your experience of this very moment, of reading these words, is not happening in a container of space and time. It is the container itself, a rich, dynamic pattern emerging from a vast, interconnected network of information at the boundary of reality. This redefines our place in the cosmos. We are not just inhabitants of the universe. We are expressions of its deepest code, living narratives written on the edge of everything. The profound puzzles we have encountered all point to a single, glaring gap in our understanding. To truly grasp what happens at the edge of a black hole, where gravity is immense and quantum effects are significant, we need a theory that can unite the two great pillars of 20th century physics. We need a theory of quantum gravity. General relativity paints a beautiful picture of the cosmos on large scales, describing the smooth, curving geometry of spacetime. Quantum mechanics provides the flawless rulebook for the subatomic world, a realm of probability and discrete packets of energy. Yet at the singularity of a black hole, and arguably at the event horizon itself, these two theories meet and produce nonsense. They are incompatible, speaking different mathematical languages about the same point in reality. Resolving this conflict is not just an academic exercise. It is the quest to discover the fundamental rules that govern reality at its most extreme, where the very concepts of space and time may be born from something deeper. Leading candidates for this unified theory sound like concepts from a philosopher's dream, yet they are grounded in rigorous mathematics. String theory, for instance, proposes that the fundamental constituents of the universe are not point-like particles, but incredibly tiny, vibrating loops of energy. In this framework, every particle we know, from electrons to photons, is a different note played on these microscopic strings. The vibrations occur in a spacetime that has more than the 3 spatial dimensions we experience, with the extra dimensions curled up into sizes far smaller than an atom. This elegant idea naturally includes gravity, with the graviton, the hypothetical particle that carries the gravitational force, arising as a specific vibrational pattern. Another profound approach is loop quantum gravity. It takes a different path, suggesting that spacetime itself is not smooth and continuous, as Einstein described, but is woven from a fabric of tiny, discrete loops. Picture the fabric of reality not as a smooth sheet, but as a network of interconnected threads, a cosmic mesh with a finite, granular structure. In this view, there is a smallest possible unit of space, a quantum of volume, and a smallest possible unit of time. These approaches force us to radically rethink the nature of a black hole's edge. In both string theory and loop quantum gravity, the classical idea of a perfectly smooth, sharp event horizon, a mathematical line in the sand, likely breaks down. Instead, it may be replaced by what physicists sometimes call a fuzzy horizon or a firewall of intense, scrambled quantum information. This region would not be a clean boundary, but a turbulent transition zone where the smooth geometry of general relativity dissolves into the frenetic quantum activity underneath. This fuzziness could provide the mechanism to resolve the information paradox. Information falling into the black hole might not be lost behind a one-way curtain, but could be chaotically encoded or even reflected at this quantum gravitational boundary, preserving the universe's quantum ledger. More dramatically, the terrifying singularity at the black hole's center, that point of infinite density, might simply not exist in a complete quantum gravity theory. The discrete, granular nature of spacetime could prevent the infinite collapse, turning the singularity into a supremely dense but finite core of quantum spacetime foam. The journey inward would not end at a point of oblivion, but would transition into a new phase of existence governed by these unknown rules. This leads to the most revolutionary possibility of all, a new description of how time itself operates at these scales. In a granular spacetime, time may not flow like a river. It might tick forward in discrete, indivisible moments, like the frames of a cosmic film. Or perhaps time is not a fundamental ingredient at all, but an emergent property that arises from something more basic, like the quantum entanglement between particles. In this view, the connectedness of things across space is what creates the illusion of a continuous, flowing time. The extreme slowing and freezing of time we witness from outside a black hole would then be a dramatic, large-scale effect of this underlying quantum architecture. The black hole's edge becomes more than a cosmic curiosity. It becomes the ultimate laboratory, the key to a grander cosmic theory. By probing its mysteries, we are not just learning about the fate of matter. We are reading the first few lines of the universe's operating manual, discovering the principles from which space, time, and gravity themselves are woven. The answers we find there will not just explain black holes, they will redefine our understanding of everything. This connection between time and disorder reveals a startling truth about black holes. They are not cold, dead-end points, but dynamic objects with a temperature. This realization came from weaving together 3 seemingly separate branches of physics: gravity, quantum mechanics, and thermodynamics. Thermodynamics is the science of heat, energy, and the one-way direction of certain processes, famously captured by the second law. It states that the total entropy, or disorder, of a closed system always increases over time. This gives us the arrow of time, the reason we remember the past but not the future. A shattered glass does not spontaneously reassemble because that would decrease entropy, violating this fundamental cosmic rule. For the longest time, black holes were seen as the ultimate exception to this rule. You could throw a whole library, a complex, low-entropy system, into a black hole, and it would vanish, seemingly erasing that entropy from the universe. This was a paradox. Jacob Bekenstein, a young graduate student, proposed a radical fix. What if a black hole itself possesses entropy? He suggested that its entropy is not related to its volume, but to the surface area of its event horizon. The more massive the black hole, the larger its horizon and the greater its entropy. This was a profound insight. It meant that when you throw that library into the hole, the horizon area increases slightly, adding enough entropy to the universe to compensate for the lost order of the books. The total entropy still goes up, preserving the second law even in the face of a cosmic vacuum cleaner. But if a black hole has entropy, a thermodynamic property, then by the laws of thermodynamics, it must also have a temperature. Anything with a temperature emits radiation. Yet how could a black hole, the ultimate trap for light, possibly glow? This is where Stephen Hawking made his monumental contribution. He applied quantum mechanics to the curved space just outside the event horizon and discovered the mechanism we now call Hawking radiation. That faint quantum glow gives a black hole its precise temperature, a temperature inversely proportional to its mass. A stellar mass black hole has a temperature barely above absolute zero, while a tiny, hypothetical black hole would be incredibly hot. This completed the picture. A black hole is a thermodynamic object. It has entropy proportional to its horizon area. It has temperature revealed by Hawking radiation, and this thermodynamic identity imposes a powerful arrow of time even on this seemingly timeless entity. The Hawking radiation process is inherently one way. A black hole slowly evaporates, its mass decreasing, its horizon shrinking over eons. But you do not see a reverse process where a cloud of radiation spontaneously collapses to form a black hole. The universe moves from a state of a massive black hole to a state of dispersed radiation, a clear increase in overall entropy. This means the edge of a black hole is not just a place where time slows down from a distant perspective. It is a place where the irreversible flow of cosmic time, the very tendency of the universe toward disorder, is physically manifest. The horizon is not a passive boundary. It is an active, encoding surface whose growth and eventual evaporation are chapters in the universe's story of increasing entropy. So when we witness the infinite time dilation at the edge, we are seeing more than a geometric curiosity. We are seeing a signpost for time's arrow, etched into the fabric of spacetime by the relentless logic of thermodynamics. The freezing of a falling object from our view is a dramatic symptom of a deeper truth, that even in the darkest corners of reality, the universe remembers which way time flows, and disorder always, inevitably, increases. To peer into these violent mergers, we must turn from telescopes to processors, from observation to pure mathematics in motion. Since we cannot stage a collision of black holes in a lab, scientists have built a digital alternative, a field called numerical relativity. This is the art of translating Einstein's beautifully complex field equations into a language supercomputers can understand, allowing them to simulate the very fabric of spacetime as it twists, tears, and heals. Imagine giving a computer the most intricate dynamic sculpture imaginable, one made not of clay but of geometry itself, and asking it to predict how that sculpture will morph and vibrate when struck. That is the monumental task of these simulations. They begin with the initial conditions, two black holes orbiting each other in the void. The code then calculates, step by minuscule step, how their immense masses warp the shared spacetime between them, how they spiral inward, and finally how their two distinct event horizons stretch, merge, and settle into a single, quivering new horizon. It is a digital ballet of gravity where every frame is a snapshot of reality's underlying geometry. But these simulations do more than show us shapes. They track the ripples. As the black holes whirl and merge, they churn the spacetime around them, sending out powerful waves in the fabric of the cosmos, gravitational waves. The simulations predict the precise shape and frequency of these waves, a unique signature encoded with information about the masses, spins, and dynamics of the colliding objects. This is why numerical relativity is not just a theoretical exercise. It is the essential decoder ring for real-world observations. When the LIGO and Virgo detectors here on Earth feel a subtle shudder in space-time, a signal that lasted less than a second, scientists compare that signal to a vast library of supercomputer-generated templates. By finding the match, they can read the story of the collision that happened billions of light-years away, determining the sizes of the black holes, how fast they were spinning, and even confirming that the final object settled down as Einstein's theory predicts. Furthermore, these digital laboratories let researchers perform thought experiments we could never conduct in reality. They can simulate the fate of a star or a cloud of gas as it falls toward a merging black hole system. From the safety of the simulation, they can watch from multiple vantage points how the infalling matter is stretched and heated, and how its light is redshifted and its apparent time slowed to a crawl as it approaches the tumultuous edge. They can visualize the extreme warping from the perspective of a distant observer and from the frame of the doomed matter itself, providing a complete, dynamic picture of how time behaves in these cataclysmic events. Without these supercomputer simulations, the faint chirps detected by LIGO would remain mysterious cosmic ticks. With them, we can translate those ticks into a detailed narrative of creation, a story where black holes dance, merge, and send whispers across the universe, whispers that tell us not just about the objects themselves, but about the severe and malleable nature of spacetime where they reside. These faint shudders in the cosmos carry a direct imprint of warped time. When two black holes spiral toward their final embrace, they churn the fabric of spacetime with unimaginable force, sending out ripples that stretch and squeeze everything in their path. These are gravitational waves not made of matter but of geometry itself. Their detection by observatories like LIGO and Virgo did more than confirm a century-old prediction. It gave us a new sense, a way to hear the universe. We are no longer limited to observing light. We can now listen to the vibrations of space-time, and the songs they sing are of gravity's most extreme domains. Each wave that passes through our planet encodes a detailed story of its violent birth. By analyzing the subtle changes in the signal's frequency and amplitude over time, scientists can decode a cosmic fingerprint. That characteristic rising tone, often called a chirp, reveals the masses of the colliding black holes, how fast they were spinning, and even the nature of the spacetime they were tearing through just before they merged. This data is our most direct probe into the regime where time behaves so strangely. The final, frantic orbits before collision, where the black holes whip around each other at a significant fraction of light speed, represent a frenzy of relativistic effects. Time dilation here is not a subtle curiosity. It is monumental, woven into the very dynamics of the inspiral. The precise way the orbit decays, the timing of the final plunge, all of this information is stamped onto the gravitational waves that travel for millions or billions of years to reach us. When we detect that chirp, we are not just hearing a crash. We are listening to a recording of time itself being stretched and twisted in the maelstrom around two event horizons. It is a direct physical message from the edge, telling us that the bizarre slowing and warping of time we have discussed is not theoretical. It is an active, dynamic player in the most energetic events since the Big Bang. This new auditory window onto the universe allows us to test general relativity in its most severe strong field limit. asking whether our understanding of time and gravity holds true even in these catastrophic collisions. This idea of a hidden, chaotic core leads us to a profound cosmic safeguard. Roger Penrose, one of the great architects of black hole physics, proposed a principle that might be a fundamental rule of our universe, the cosmic censorship hypothesis. In essence, it is a statement about what the cosmos allows us to see. The hypothesis suggests that nature abhors a naked singularity, that terrifying point of infinite density, where all known laws of physics cease to function, must always be dressed in an event horizon. It must be clothed, hidden from the view of the outside universe. A black hole is the acceptable form, a singularity politely veiled behind its dark curtain. But what if that curtain were torn away? The result would be a naked singularity, an infinitely dense point of mathematical madness exposed to the rest of the cosmos. And according to the mathematics of general relativity, such an exposed singularity would be a calamity for reality as we understand it. Without the protective barrier of an event horizon, the extreme warping of spacetime around the singularity would be accessible. The closed timelike curves we discussed earlier, those theoretical loops in time, would not be confined to an inaccessible interior. They could extend out into the universe at large. This would make time travel to the past not just a speculative idea, but a potential physical possibility in that region. You could, in principle, encounter your own past self. The orderly chain of cause and effect, the principle that a cause must always come before its effect, would completely break down. Physics, the science of prediction, would become impossible. The future could influence the past, creating paradoxes that unravel logical consistency itself. Penrose's hypothesis is a bold claim that our universe has a built-in protection against this chaos. It proposes that the initial conditions of the cosmos and the laws of physics as they play out simply do not permit naked singularities to form. Any singularity that emerges from realistic conditions, like the collapse of a star, will always be modestly dressed in an event horizon. This transforms our understanding of that dark boundary. The event horizon is not merely a trap, it is a cosmic guardian. Its primary role may be to quarantine the destructive unpredictability of the singularity, to shield the rest of the universe from its causal poison. By containing the region where time and space lose all meaning, the horizon preserves the orderly flow of time and the reliable structure of cause and effect in the observable cosmos. It is the reason we can do science at all. It ensures that from our vantage point, the universe is predictable and coherent. The infinite time dilation we witness at the edge is not a glitch, but a symptom of this protective barrier at work, a sign of spacetime bending all possible paths away from the chaotic interior. While the cosmic censorship hypothesis remains unproven, it is a powerful guiding principle. It suggests that the strange freezing of time at a black hole's edge is the universe's way of drawing a line, a permanent boundary beyond which the familiar rules are suspended, not to harm the outside world, but to protect it. The horizon is the ultimate firewall, not of energy, but of causality itself. But the mathematics of general relativity sometimes points to a mirror image of this darkness. If a black hole is a one-way door inward, a cosmic drain from which nothing escapes, its theoretical opposite would be a white hole. Picture a cosmic fountain, a region of spacetime from which nothing can enter, but matter and energy can only erupt outward. While black holes are thought to be realistic endpoints for massive stars, white holes are purely hypothetical creatures that appear when we extend the equations for black holes backward in time. They are not objects you could find, but mathematical possibilities that force us to confront a deep question about the fabric of reality. Our laws of physics, at their most fundamental level, are often time-symmetric. The equations work just as well if time runs forward or backward. Yet our lived universe is clearly not symmetric. We remember the past, not the future. A cup shatters, but the pieces do not leap back together. This one-way street is governed by the second law of thermodynamics, the increase of entropy or disorder. A white hole, by constantly spewing out ordered matter without any apparent input, would violate this law. It would be like watching a movie of an explosion played in reverse, with all the debris flying perfectly back into a pristine bomb. The universe as we know it simply does not run that way. So why even consider them? Because they serve as a brilliant thought experiment. They throw the strange behavior of time at a black hole's edge into stark relief. We saw that from an outside perspective, an object approaching a black hole appears to slow, redden, and freeze at the event horizon. Now run that film backward. The time-reversed version would show an object appearing from nowhere, already hovering at the edge of a white hole, then bursting forth into the universe in a brilliant, blue-shifted flash, its clock seeming to tick infinitely fast from our point of view. The infinite time dilation is inverted into an infinite time eruption. This theoretical mirror highlights what is perhaps the most important lesson of all. The extreme warping of spacetime allows for these bizarre symmetries in the math, but our actual lived cosmos picks a direction. Entropy gives time its arrow. The freezing at the black hole's edge and the impossibility of a white hole's existence are two sides of the same coin, both testaments to the fact that the universe is moving from a state of order to disorder, and that irreversible flow is woven into the very geometry we have been exploring. The black hole's horizon is not just a boundary in space, but a monument to time's one-way journey. The astronaut's own clock tells a different story entirely, one of swift and violent finality. From the moment they cross the event horizon, their personal measure of time, what physicists call proper time, begins a brief and terminal countdown. For a stellar mass black hole, this final journey from horizon to singularity might last only a few milliseconds. In that fleeting span, their perception remains local and normal. Their heartbeat, their thoughts, the ticking of the instruments on their suit all proceed at the familiar, steady rhythm of a second per second. There is no sudden jerk, no dramatic cinematic shift. The crossing itself, from their perspective, is an uneventful passage through an invisible mathematical surface. Yet the universe they leave behind undergoes a radical transformation. If they were to look back, outward toward the cosmos they came from, the view would be both breathtaking and terrifying. All the light from the external universe, struggling to catch up to them as they fall inward, would be compressed. The wavelengths would shorten dramatically, shifting the entire sky into a blaze of blue and ultraviolet, focused into a brilliant, shrinking disk of light directly behind them. It would be like watching the entire history of the cosmos, from the present moment back toward the beginning, playing out in a hyper-accelerated blur. Galaxies would streak, stars would flare and die, all compressed into those final milliseconds of perception. This is the view from a plummeting frame of reference, where the external universe appears to rush into the future at a fantastic rate. Meanwhile, the descent ahead grows increasingly severe. Those tidal forces we discussed earlier, the difference in gravity between head and feet, cease to be a theoretical gradient and become an immediate physical reality. In these last moments, the stretching becomes overwhelming. The astronaut and their craft would be pulled into a strand of atoms, a process completed well before the final destination. This personal timeline is stark, finite, and intensely physical. It stands in utter contradiction to the eternal, frozen tableau witnessed from a safe distance. One reality holds a swift, if violent, conclusion. The other holds an everlasting ghost suspended at the brink. Both are true descriptions of the same event, a demonstration of relativity's most profound lesson, that time is not a universal river but a personal path, and your experience of its flow depends entirely on the gravity of your situation. Yet the stage upon which these cosmic dramas unfold is built from deeper, more pervasive mysteries. Our journey into the warped time around black holes has focused on local, extreme distortions. But to fully appreciate their place in the cosmos, we must pull our view back to the grandest scale. The universe itself is not a static theater. It is an expanding, evolving arena whose very structure and fate are sculpted by two invisible architects, dark matter and dark energy. These enigmatic components make up over 95% of everything that is, yet we have never directly seen them. Their presence is known only by their gravitational effects on the things we can see. Dark matter acts as the cosmic skeleton. Its gravitational pull provides the scaffolding that allowed galaxies and galaxy clusters to form in the early universe. It exists in vast, diffuse halos that envelop galaxies like ours, its gravity holding the swirling stars together. Dark energy is something else entirely, a repulsive force that permeates the vacuum of space itself. It is causing the expansion of the universe not just to continue, but to accelerate, pushing galaxies apart from one another at ever-increasing speeds. This is the cosmological context. Black holes are not isolated monsters in a void. They are players on a stage whose size, shape, and future are dictated by these dark, dominant forces. The supermassive black hole at the heart of our Milky Way, Sagittarius a star, did not form in isolation. It grew over billions of years, feeding on gas and merging with other black holes, all within the immense gravitational well of our galaxy's own dark matter halo. That halo guided the formation of the galaxy, which in turn funneled material toward the center, feeding the black hole. They co-evolved, the visible galaxy and its dark heart, shaped by the invisible dark matter that binds them together. On the largest scale, dark energy sets the ultimate destiny. As the acceleration of the universe's expansion continues, distant galaxies will eventually be pushed so far away that their light can no longer reach us. The cosmic horizon will shrink, in a future so distant it defies comprehension. Any civilizations that might arise will see only their own galaxy in an otherwise black, empty sky. And what of black holes in that lonely, expanding future? Their fate is tied to this cosmic timeline. Over epochs far longer than the current age of the universe, they will slowly evaporate via Hawking radiation, their mass converting to a faint mist of particles. But the relentless pull of dark energy may stretch the very fabric of spacetime so thin that this final evaporation becomes the last meaningful event in vast, isolated pockets of reality. This grand context offers a humbling perspective. The extreme freezing of time at a black hole's edge, while breathtaking and profound, is a local phenomenon. It is a dramatic whirlpool in the cosmic ocean, but the ocean itself has its own currents and tides set by the dark universe. The arrow of time we experience every day, the one that points from the ordered past to the disordered future, is powered by the increase of entropy on a universal scale, an expansion and cooling driven in part by these dark components. So when we ponder the warped clock at the event horizon, we are examining an exquisite, severe detail in a much larger and still mysterious portrait. Understanding the local rules of gravity's extreme theater is essential, but the final act of the cosmic story will be written by the dark. This scrambling process has its own clock, a distinct timescale set by the black hole's size. For a stellar mass black hole, information might be scrambled in mere microseconds. For a supermassive giant like Sagittarius a star, the process could span hours or days. This is not an arbitrary delay. It is a fundamental computational step, the time required for the quantum bits on the horizon to become thoroughly entangled with one another, erasing any trace of the original order. From this viewpoint, the infinite time dilation we witness from afar is more than a relativistic curiosity. It represents the ultimate processing bottleneck. As a bit of information approaches the event horizon, from our perspective, its interaction with the scrambling system appears to slow to a halt. It is as if the input to the cosmic computer is taking an infinite amount of time to be registered, because the act of being processed is inextricably linked to the severe warping of time itself. The frozen astronaut is not merely stuck in time. They are a piece of data suspended at the input terminal of the most powerful processor in the universe, awaiting its turn in the queue. This computational metaphor reframes our deepest questions. The black hole information paradox becomes a question about data preservation and retrieval in a system where time and information are fundamentally linked. The holographic principle is the operating system, and Hawking radiation might be the thermal noise emitted by the intense processing activity. Even the arrow of time, the irreversible flow from order to disorder, could be seen as a consequence of this one-way computational process, where information is constantly being encoded into a more complex, scrambled state from which it cannot easily return. While this remains a theoretical framework, it offers a powerful and strangely intuitive lens. It suggests that the cosmos at its most extreme may not be governed by forces alone, but by logic and computation. The edge of a black hole is not a passive boundary. It is an active processor, and the bizarre behavior of time there is the most visible signature of its relentless, inscrutable work. The clocks in our lives are not all synchronized. On our own planet, a precise atomic clock placed on a mountain will run a tiny, almost imperceptible fraction faster than an identical clock at sea level. This is not a mechanical flaw. It is the whisper of gravitational time dilation, a real and measurable effect where time flows more slowly where gravity is stronger. The clock at the lower altitude sits deeper in Earth's gravitational well, and its ticks are stretched by the planet's gentle pull. The difference is minuscule, but it is there, a quiet testament that even our familiar world bends the fabric of time. Now take this subtle effect and amplify it beyond all earthly scales. A black hole is not a gentle well, it is a bottomless chasm in space-time. Approaching its event horizon is like descending into a gravitational abyss of infinite depth. The slowing of time is no longer a whisper, it becomes a deafening, all-consuming reality. To make this cosmic extreme relatable, we can stretch our everyday experiences. Think of sending a simple text message. From your phone to a friend's, the data travels in a crisp, instant burst of ones and zeros. Now, imagine trying to send that same message from a probe hovering near a black hole's edge. Each bit of data, each pixel of the emoji you attached would have to climb out of that immense gravitational pit. The signal would be stretched into an agonizingly slow stream. The first letter of your message might arrive, and then you would wait an age for the next one. From the perspective of your friend waiting light years away, your simple hello would be drawn out into an infinitely long, fragmented sigh, each piece separated by eons. This analogy helps bridge the vast gap between our normal reality and the physics of the extreme. It translates an abstract, mathematical infinity into a more tangible idea of a process slowing to an absolute crawl. The frozen astronaut we picture is not just stuck in a pose. They are a living message whose final transmission to the universe has been stretched into a single, never-ending moment. These comparisons do not diminish the strangeness, they give our intuition a foothold. They allow us to grasp that the laws governing our world do not break at the edge of a black hole. They are merely pushed to a limit so far beyond our daily experience that they reveal a universe far more malleable and interconnected than we ever dreamed. The ultimate answers will not come from theory alone, but from a new generation of eyes and ears trained on the cosmos. Our quest to understand time at the edge of eternity is driving the creation of revolutionary observatories, instruments that will transform whispers into symphonies and shadows into dynamic films. In the silent expanse between worlds, a mission called the Laser Interferometer Space Antenna, or LISA, is taking shape. This is not a single telescope, but a trio of spacecraft flying in a perfect triangular formation millions of kilometers apart. They will form the most sensitive gravitational wave detector ever conceived, one free from the rumbling interference of our planet. While ground-based detectors like LIGO listen to the high-pitched chirps of stellar mass black holes, LISA will tune into the lower frequencies of the universe. Its primary target is the slow, stately dance of supermassive black holes, orbiting each other for millions of years before their final, cataclysmic merger. By detecting these waves, LISA will map the geometry of spacetime around these giants with exquisite precision. It will hear the final inspiral, the merger, and the ring down as the new, single black hole settles into its form. In that signal, scientists will search for deviations, tiny wobbles or echoes that could hint at new physics, perhaps even signs of a quantum structure to spacetime itself. This will be our most direct probe yet into the warped geometry where time behaves so strangely. Meanwhile, back on Earth, the Event Horizon Telescope collaboration is not resting on its laurels after that first historic image. The plan is to expand the network with new telescopes in strategic locations and to observe at even higher frequencies. The goal is breathtaking: to move from a single, iconic snapshot to a full-fledged movie of a black hole. Imagine watching a bright knot of plasma in the accretion disk of Sagittarius, a star, as it completes an orbit. In flat space, that orbit might take minutes. But through the lens of the Event Horizon Telescope, we would see that motion dramatically slowed, stretched out over hours due to the extreme gravitational time dilation. We could potentially witness the subtle effects of frame dragging, the way the spinning black hole twists spacetime around it, by tracking how these blobs of light are pulled along in the cosmic whirlpool. These are not just better pictures, they are direct visual tests of general relativity in the strongest possible fields. They will allow us to watch the predictions of frozen time and warped space play out in real time across the galaxy. Together, these next-generation instruments represent a fundamental shift. We are moving from verifying that black holes exist to studying how they live and breathe. From confirming predictions to searching for the cracks in our theories, each unexplained flicker in an Event Horizon Telescope movie, each anomalous frequency in a LISA signal, could be a clue. It might point to where Einstein's magnificent theory of gravity, which has guided us so far, begins to show its limits. It could reveal the first observational hints of what lies beyond, the quantum gravitational rules that must take over at the very edge of reality. The frozen time we have been exploring is not the end of the story. It is a signpost, and these new observatories are our vehicles, built to take us down the road it points toward, into a future where the universe's deepest secrets about time, space, and gravity may finally come into focus. The universe has no obligation to conform to our sense of what is meaningful. When we confront the reality that time itself is a personal, pliable experience, it gently dissolves some of our most cherished anchors. The idea of a fixed destiny, a predetermined path laid out on a universal timeline, loses its footing in a cosmos where timelines are relative and can diverge so dramatically. If an astronaut century and our own can pass at wildly different rates, then the notion of a single, linear fate for all things becomes a local story, not a cosmic rule. This does not erase free will but reframes it. Our choices are not playing out on a rigid, universal stage, but on the personal, curving path of our own world line through the flexible fabric of spacetime. Every decision we make writes the next step of that unique path, a narrative thread woven into a much larger, more complex tapestry where cause and effect remain intact, even as the tempo of the story changes from place to place. This perspective can feel unsettling, yet it is also liberating. It suggests our lives are not tiny, pre-scripted roles in a vast, indifferent play. We are active participants, navigating a reality that is far more dynamic and interactive than we ever imagined. Our brief human lifespan, perhaps a single century against the eons of cosmic evolution, takes on a new character. Compared to the near-infinite time dilation at a black hole's edge, our existence is a flicker, a spark that appears and vanishes in an instant. This could be seen as a recipe for insignificance, but it is precisely the opposite. That fleeting nature is what makes our moment of awareness so astonishing. In a universe that can stretch a second into an eternity, the fact that we are here at all, conscious and curious within our narrow window of time, is a profound and unlikely gift. It means every experience, every connection, every discovery we make is not diminished by the scale of the cosmos, but heightened by it. We are the universe becoming aware of itself, if only for a short while. This understanding humbles us, yes. It reminds us that our intuitive reality of a steady, shared time and a three-dimensional world is just a comfortable, local slice of a much stranger and more magnificent whole. Our everyday perception is like living our entire lives in a single, quiet valley, never suspecting the existence of towering mountains or deep ocean trenches beyond the horizon. Black holes are those mountains showing us the true, extreme topography of reality. And yet, our greatest testament is not in feeling small, but in our relentless capacity to reach beyond that valley. The very fact that we can comprehend these mysteries, that we can use mathematics and observation to grasp the warping of time at the edge of oblivion, is a triumph of the human spirit. It proves that our consciousness, born in this gentle gravitational backwater, can extend its understanding across the galaxy and into the heart of the most severe phenomena. We are not just passive inhabitants of spacetime. We are its cartographers, slowly and patiently mapping its contours, from the familiar hills of our planet to the sheer cliffs of a black hole's event horizon. In doing so, we do not find a universe that devalues our existence. We find one that makes our quest for meaning, our drive to understand, the most significant story of all. Our journey has brought us to the edge of understanding, but the map still has blank spaces marked by profound mysteries. Despite the breathtaking advances in observation and theory, the black hole's horizon remains a frontier where our knowledge dissolves into a fog of unanswered questions. We have described the event horizon with the smooth geometry of general relativity, but what is its true nature at the quantum scale? Is it a sharp mathematical boundary, or a seething, fuzzy layer of spacetime foam, buzzing with unimaginable energy at the Planck scale? This question is not just about a location, it is about the fundamental ingredients of reality. If spacetime is granular, then the horizon must be too, and its microscopic structure could hold the key to how information is preserved, scrambled, or perhaps even reflected. Then there is the ultimate fate of what falls in. Hawking radiation provides an elegant mechanism for a black hole to evaporate. But does it truly carry the information of the swallowed library, the lost astronaut, the history of everything consumed? Or is that information irretrievably lost, violating the quantum law that says it must be preserved? The debate between information loss and unitarity is not an academic squabble. It is a battle for the soul of physics, a choice between a universe that forgets and a universe that eternally remembers, even if in a form we cannot easily read. The answer will dictate whether cause and effect remain sacred at the cosmic scale. Our equations allow for even wilder possibilities, like stable wormholes or those closed Timelike curves paths that loop back on themselves in time. But are these mere mathematical phantoms, or could they exist in some corner of a multiverse, governed by laws we have not yet discovered? The fact that our best theory of gravity even permits such ideas tells us that the nature of time is far more fluid than our daily experience suggests. Yet turning that mathematical permission into physical reality seems to require miracles like exotic matter with negative energy, whose existence remains purely speculative. Beneath all these puzzles lies the grand, unifying challenge, the singularity. This is the point where the graceful curves of general relativity meet the frenetic probabilities of quantum mechanics, and both theories break down, offering only infinities and contradictions. Uniting these two pillars into a single framework of quantum gravity is perhaps the greatest intellectual quest in modern science. It is the search for the rulebook that governs reality at its absolute beginning and its most extreme ends. Solving it would not just tell us what happens at the center of a black hole, it would reveal the fundamental code from which space, time, and matter are woven. These are not dead ends but beacons. Each unanswered question about time at the black hole's edge is a call to adventure for the next generation of thinkers. They are the compelling mysteries that drive physicists to develop new mathematics, to dream of experiments that span solar systems, and to dare to conceive of concepts we do not yet have words for. The strange freezing of time we have explored is not a final answer. It is a profound clue, a signpost pointing toward a deeper layer of reality, waiting for us to learn how to see it. Our journey to the edge of a black hole has revealed a realm where time is not a constant river but a malleable fabric, stretched to its limits by gravity's immense power. From the foundational warping of spacetime to the paradoxical experiences of different observers, from the quantum whispers of Hawking radiation to the philosophical upheavals, we have seen how this extreme environment challenges and enriches our understanding of reality. The black hole serves as both a cosmic laboratory and a mirror, reflecting the profound and often counterintuitive truths of our universe. As we continue to observe, simulate, and theorize, remember that each mystery solved unveils deeper questions, driving the eternal human quest for knowledge. If this exploration of time's strange behavior has captivated you, consider subscribing for more deep dives into the universe's greatest puzzles, and share your thoughts on these temporal wonders in the comments.